Welcome back to our series on probability theory. I'm Mark Ledbetter. This is lecture video 38, part B, and we are discussing conditional probability distributions. This is part 2. Last time we introduced a conditional PDF or PMF, both of those, and we talked about the properties of these conditional PMFs, and we compared the discrete and the continuous versions. So I've decided that statistical bias will wait until next semester. It goes better in one of the topics in Stat 333, which is our mathematical statistics course. So we're going to do some examples and maybe get to correlation and regression, but I think that'll be in part 3. So we have this continuous example. We have the joint PDF, f of xy is equal to 2 when x is between 0 and y. So what we do here is we're going to first isolate x, and x is between 0 and y. And then we can isolate y, and we see that y is between x and 1. So in the middle, we see the relationship between x and y. And so x is less than y, so I need the line y is equal to x, and then I need to get my boundary. So if I take x is 1/2, then that point is 1/2, 1/2, y is 1/2, x is 1/2, and I need x to be less than y. So y is 1/2, x needs to be less than 1/2, so it needs to be over here, but it has to be within the line. So x is actually going to be in the shaded region, so this is going to be the shaded region. So that is going to be our R for this problem. Okay, so that is R, our range, joint range of x and y. Now, we need the boundaries for each side, and so here we have that this is x equals 0, and this line is y equals 1, and then we have y equals x as the dotted line. And as I mentioned here, of course, this is critical to solving the problem, having this joint range. So f of x, the the marginal distribution of x, is going to be the integral of the joint with respect to y, across y. And so as we can see, when we're integrating an x, we go from x equals 0, or actually this is y, so we go from y equals x up to y equals 1. And so that's what we have here. F of xy is 2, dy gives us 2, 1 minus x for x between 0 and 1, 0 otherwise. Now the marginal of y, we do similarly. We come out with 2y when y is between 0 and 1. I've also included e of y here and e y squared here. So e of y is 2/3, e y squared is 1/2, and the variance of y is 1/18. Please work through that and make sure that you understand. So it turns out that f of xy is the uniform between 0 and y. So it says C below, so I've worked this out so we can see what this looks like. So here is f of x given y, and we use the definition, f of xy over f of y, and can use that. And so it's 2 over 2y, so this is 1 over y, and when x is between 0 and y. Now, this is uniform between 0 and y, if this is y. Then this area, and it's supposed to be a rectangle. Let's see if I can draw it a little bit better. Not much, but pretend this is a rectangle. So this area here under the line has to be 1. And so it turns out that if I take this distance y, so this is 0, so that distance is y, and then this distance here, I multiply them, they have to equal 1. So I've got f of y here, and so f of y times y equals 1. And so I solve for f of y, and f of y is 1 over y. And so that's a uniform between 0 and y. And that's what we have here. Now, likewise, we find out that the conditional distribution of y given x is a uniform between x and 1. And so I've worked that out here as well. F of x, y over f of x. And that's 2 over 2, 1 minus x, which the 2's cancel and give me 1 over 1 minus x, x between y and 1. And so that, again, is the difference between here and here is 1 minus x. So I have a rectangle between 1 and x, and the height has to be 1 over 1 minus x for this area here to be 1, because it's a probability distribution, so the area under the curve is always 1. So that's how I know that this is a uniform between y equals x and 1. All right? So remember, y is the variable and x is a constant here. All right? So that's the reason. Now, using the fact that f of x given y is a uniform, I know that the expected value, the mean, is simply the 0 plus y over 2. I can use that and get y over 2, and where y is between 0 and 1. Or I could work it out longhand, and that's what I've done here. I've taken the integral of x times f of x given y dx, and of course it's going to be from 0 to y. Those are my limits. And then this works out, f of x given y was 1 over y, so I have x over y dx. I'm integrating with respect to x, so I get x squared over 2. So this turns out to be x squared over 2y. X is going from 0 to y, so this turns out to be y squared over 2y, or y over 2. So again, it works out the same both ways. Now, I'm just going to use the fact that I know this is a uniform for e of y given x, and so that's x plus 1 over 2. So I take this plus this divided by 2, and x is between 0 and 1. And I see I went out of order, but variance of x given y is the variance of a uniform 0 to y, so that is y minus 0 squared over 12, so y squared over 12, 0 to y. So that's a lot faster than going through the calculation, but you could get there going through the calculation as well. All right? So you figure out e of y given, e of x squared given y, e of x squared given y, and you can find variance of x given y. Now, the variance of y given x, in this case, we have the uniform again, but from x to 1. And so we take 1 minus x, quantity squared over 12. Again, the variance of the continuous uniform distribution. And x is between 0 and 1. Now, we want to find the expected value of the variance of x given y. And so this is the expected value, and we've already given the variance of x given y. We already found that up here, and that was y squared over 12. So that's e of y squared over 12. And that is going to be 1/12 e of y squared. And we figured out y squared was 1/2. And so that's 1/12 times 1/2, which is 1/24. Now, the variance of e of x given y is the variance of y over 2, because e of x given y we found out was, I'm going to clean this up a little bit. It's right here. So y over 2. So variance of y over 2. So I can rewrite this as variance of 1/2 times y. And so I have a constant. A constant becomes squared and pulls out to the front. That's the rule that we found out about the variance of something. And we use the covariance. If you don't remember this, the variance is the covariance. So this is of itself. So the variance is y over 2, covariance of y over 2, comma y over 2. So this is the covariance of 1/2 y with 1/2 y, and so I have this constant and this constant, so that's, I have to bring both of them out and multiply in the front, and that gives me the 1/4. All right? So we're using all the properties that we've learned so far, and that's why I wanted to do this, do the continuous well, we had to do correlation and with the covariance before we did the conditional. All right. And so so the variance of y over 2 is going to be 1/4 the variance of y. The variance of y we figured out was an 18th, so this is 1 over 72. Now the variance of x is e of variance x given y plus variance of e of x given y that we figured out these two values, 1/24 and 1/72. So we work out the common denominators, and so that's 3 times 24 is 72, and so we have 4 over 72, or 1 over 18. And we can check some of this with some of the things that I did. Here's ex squared, here's ex, here's the variance of x, and so we've checked some of these and variance of x. So I've done this the other way and came out with 1 over 18, so it's the same exact answer as it should be. And 12, e of x, so I can use, without calculating this directly, because I don't believe we did anywhere, then I can simply say e of x given y. That's going to give me e of x. And e of x given y, we figured out was y over 2, and so that's going to be 1/2 e of y, but we can actually use the marginal here and do the integral and find out that it's 1/3. And again, we can check that by doing using the marginal of x times, so x times f of x. And when we work that out, of course, we get the same answer, 1/3. All right, so that is an example of how we would do the problems in this section. So I hope that that helps you. Of course, I did use the shortcut for the uniform here several times, but I also tried to write out the long way when I could think about it, so when I had the chance. So you can always, go back to the definition, because this was a special case where the uniform, we turned out with the uniform, we know what the variances are easily with the uniform and the expected value, but you could do it longhand and come out with the same answer. So when it's not this special case, you'll have to use the formula. Okay, so please don't forget to scan and upload your lecture notes before midnight of the date listed on the course calendar. If you have questions, by all means, come to my virtual office hours. If you can't do that, then please email me. You're welcome to do that, but I need two things from you when you do that. One is a picture of your work, and the other is a picture of the problem, because if you want me to help you quickly, I may not have access to the problem, and if you send me a picture of your work, then I'll know how you're thinking about the problem, and I'll be able to help you quickly and more effectively. So please take care of yourself, stay safe, and we will see you next time.